In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single underlying force. He described this interaction through four elegant equations, establishing the definitive set of rules for how charges and fields behave. These equations were incredibly successful, providing the mathematical foundation for every pillar of the 20th century, from the first long-distance radio broadcasts to the massive power grids that electrified the planet. But we have reached a threshold where these classical applications are hitting physical limits. AI data centers are generating more heat than current cooling systems can dissipate. 5G networks are struggling with bandwidth saturation, and medical treatments often rely on broad chemical interventions because we cannot yet manipulate cells with enough precision. To move past these bottlenecks, physicists are no longer just following the standard textbook applications of Maxwell's work. Instead, they are looking for ways to bypass constraints once considered absolute. They are treating electromagnetism as an unfinished symphony, a field where the most impactful interactions are still waiting to be engineered at the microscopic and quantum scales. For over a century, electrical engineering was defined by physical limits. If you wanted to move high-power energy or massive amounts of data, you needed either copper wires or a perfectly clear line of sight. In 2025, a DARPA program bypassed the need for cables entirely, successfully beaming 800 watts of laser power across 8.6 kilometers. They achieved over 20% efficiency, demonstrating high-power energy can be delivered through the air at distances once thought impossible. We face a similar challenge with 6G telecommunications. 6G is the next generation of wireless technology, operating at terahertz frequencies to provide massive bandwidth. However, these ultra-high-frequency waves are easily blocked. Standard building materials and metals stop them cold. The solution is a technology called reconfigurable intelligent surfaces, or RIS. These are planar arrays of sub-wavelength elements that dynamically control the reflection and refraction of electromagnetic waves. As shown, when a signal hits an RIS-coded wall, the surface calculates the exact angle needed to bounce the beam around a pillar to reach its target. This turns passive urban environments into active components of a network, allowing us to steer data through complex cities as if the walls themselves were programmable. For decades, magnetic memory was trapped in a binary trade-off. Ferromagnets, like those in your hard drive, produce a strong signal but create stray magnetic fields that limit how closely you can pack data. Antiferromagnets have no stray fields, but their signals are too weak for a computer to reliably read. That classification was considered complete until the 2024 experimental confirmation of altermagnetism. Altermagnetism produces spin-split bands like a ferromagnet, but with zero net magnetization. In this manganese telluride lattice, the alternating physical orientation creates separated transport channels for spin-up and spin-down electrons. It generates a robust, readable signal without any interfering stray magnetic fields. When engineers used these properties to build a neuromorphic computer network, the system achieved 100% pattern recognition accuracy while consuming only 0.1 nanojoules of energy. This provides a way to build AI hardware that operates at terahertz speeds without the massive energy demands that currently plague data centers. Historically, medical electromagnetism required massive, room-sized machines, like this 11.7 Tesla MRI, to generate the forces needed to see inside the human body. But we are now moving toward a scale where we can observe individual cells. Researchers have developed biological qubits by coaxing proteins into a stable quantum state. A qubit is a quantum bit that uses properties like electron spin to store and process information. These protein-based sensors can now act as molecular MRIs inside a living cell. This same precision is being used for treatment through magnetomechanical stimulation, or MMS. Superparamagnetic nanoparticles, only magnetic when an external field is present, are engineered to hunt down and bind to the exterior of malignant cancer cells. When a rotating magnetic field is applied, these particles spin violently, mechanically tearing the cancer cell apart while leaving surrounding healthy tissue completely untouched. By utilizing the mechanical force of magnetism at the nanoscale, we can replace broad, toxic chemotherapy with a physical tool that eradicates disease with mathematical accuracy. Our understanding of the world is shifting towards environments where power is beamed by lasers, walls steer 6G data, and altermagnetic crystals run AI processors. The next immediate hurdle is the temperature barrier. Researchers are already demonstrating nickelate superconductors that function at ambient pressure, suggesting that the requirement for extreme cold is another constraint that may soon be bypassed. James Clerk Maxwell's 4 equations are as accurate as they were 160 years ago, but our ability to engineer them at the atomic level has completely changed. Electromagnetism is a living, evolving discipline, and its most significant surprises are still taking shape in the invisible spaces between positive and negative charge.